Ultrapure water reclamation fails in most semiconductor fabs for one reason: a single molecule that reverse osmosis cannot stop. It's called urea, and it's why millions of gallons leave the fab every day. A modern semiconductor fab draws millions of gallons of water per day. Nearly all of it becomes ultra-pure water, stripped of dissolved solids, organics, and trace ions, until it reaches roughly 18.2 megam centimeter resistivity. That water washes the wafer once, then most of it leaves the building as industrial wastewater. You would expect a fluid refined that far to be recycled indefinitely. It isn't. And the reason is not carelessness. It is a physical limit built into the filtration architecture itself. Inside the subfab, miles of high-purity piping and diaphragm valves move that water through the tool bays. In a true closed loop, water enters the supply line, washes the wafer, and returns to a reclaim system to be used again. But at the return line, the loop breaks. The stream is diverted to discharge and permanently exits the facility. To understand why, stop looking at the infrastructure and start looking at the chemistry. Conventional high-purity treatment trains capture contaminants two ways: by physical size and by electrical charge. Reverse osmosis is the size filter. Feed water is forced against a semi-permeable membrane, and molecules too large to fit through the membrane pores are rejected. Continuous electrodeionization, or CEDI, is the charge filter. It uses an electrical field and ion exchange resin to pull dissolved ions out of the stream. Together, reverse osmosis and CEDI remove better than 99% of what enters. But both mechanisms share the same blind spot: a contaminant small enough to slip through the membrane pores and carrying no electrical charge is invisible to the entire train. That describes urea exactly. Urea is a low molecular weight, electrically neutral organic compound with the formula CONH2 twice, roughly 60 daltons, carrying no net charge. It enters fab wastewater from process chemistry, from cleanroom air handling, and from human operators. Its size lets it pass through reverse osmosis membrane pores. Its neutrality makes it invisible to CEDI's electrical field. The result: 60 to 80% of urea survives a conventional treatment train intact. Ultraviolet oxidation is often assumed to cover that gap. It doesn't. UV alone removes roughly 10% of the urea present, and stacked on top of reverse osmosis and CEDI, it still leaves the majority of the load sitting in the stream. And because urea is organic carbon, it holds the water's total organic carbon above the subparts per billion ceiling that ultra-pure water requires. One molecule, present in trace amounts, disqualifies the entire stream. Here is where operating teams lose the most time. This is not a filtration performance problem, and it cannot be tuned out. Running the reverse osmosis stage at higher pressure does not reject a neutral molecule that already fits through the pore. Higher pressure simply pushes more water through the same pores, and the urea goes with it. Adding ion exchange capacity does not capture a molecule that has no charge to exchange. The fix has to sit upstream of the reverse osmosis stage. A purpose-built semiconductor reclaim train adds a pretreatment stage engineered to break neutral organics apart. Once urea is fragmented into charged species, the existing reverse osmosis and CEDI stages capture it normally, which makes this a procurement decision, not an operations decision. That pretreatment stage has to appear in the specification before the first pipe is set. On the fab floor, a standard water skid and a semiconductor reclaim skid look nearly identical. Same frame, same pumps, same housings. The difference is in the treatment architecture specified upstream. And by the time that difference shows up in a total organic carbon reading, the capital is already committed. That is the specification trap. Liberty CES works on the equipment selection side of exactly this problem, matching Axion reverse osmosis and CEDI architecture to the real chemistry of the fluid path. If your reclaim stream is holding total organic carbon and no one can tell you why, Urea is the first thing worth testing for.